Hello and welcome. In this video, I'm going to demonstrate the creation of a program for a simple motor control circuit. So here I have a basic visualization that I created in CODEYS. This has some simulated values that are being calculated and triggered by the CODEYS application. So the first thing I want to do is enable the simulation, and that will allow me to start the motor. And from there, we'll see continuity lines going from the control power running through the control circuit and then subsequently energizing the auxiliary contacts of the motor starter, which will then energize the motor coil, and that will provide power to our motor. So if I click start, you can see that I have continuity from my start push button to the auxiliary contacts of my motor. The auxiliary contacts turned white. The motor contactor also turned white, and you can see black, red, and blue lines representing the 480 volt circuit going to our motor. There's also some basic simulated values for pressure and flow. This is just a signal generator. It's not a high fidelity model or anything like that, just a signal generator so that we can see values moving. And then I have some different fault routines that I can inject. So for example, I can inject an over voltage condition, and this will start increasing the voltage until it is above the alarm limit, which will then start a timer based on this time delay. And we'll see a fault, and this will stop our motor, and you can see that I no longer have continuity after my fault going to my start button, and my motor and contactor are both de-energized. Okay, so now we will switch over to RsLogix 500 to show the process of creating the PLC program to run this code. Okay, so we've switched over to RsLogix 500 Pro, and I'm using the AWS app stream, so I'm also going to want to start my 500 emulate program, and I will also want to start my RsLinx Classic. And the first thing I always do before I start any project is configure the RsLinx emulator driver. So that's available in the available driver types. It's the SLIC 500 DH45 emulator driver. This will allow us to emulate the PLC and test our program without having a connection to a physical PLC. I always choose station 4 just to make sure I keep it separate from my PLC node. And once that's running and we confirm, we can go ahead and minimize RsLinx. And then we will start our project by choosing the MicroLogix 1100 PLC Series B. I always choose MicroLogix for emulator. It just seems to work the best. So that's been my habit. And then next we want to configure our I/O cards. So we want a 16 input card on slot 1. We want a 16 output card on slot 2. And that's all we really need for now. And then in our ladder rung, the first thing I want to do is define my alarm conditions. So my alarm conditions are going to be over voltage, over current, over pressure, overflow, underflow, and fail to start. So those are the 6 different alarm conditions that we're defining in this program. So the first alarm that we're configuring is over voltage, and I'll use a greater than or equal to instruction for that. And that is the symbol GEQ, or you can also select it from the instruction list. But if you know the shorthand, you can just type that directly into the rung. And we're going to choose an N7 register. This is a integer value, so we'll just use that as a sort of placeholder for our voltage. And then we are going to check it against a static value of 520. So this will read the value on N70. If it's greater than 520, then there will be continuity along this rung. So the next thing we want to add is a timer on, and this is going to be the first timer that's available, T40. The time base will do 1 second, and for our preset time, we'll do 5 seconds. And then we are going to add a branch around our timer so that when this timer is done, we will energize an output. So this will be T40/done, DN, and we'll call this timer our over voltage timer. And then we'll just name this OVTMR on our symbol. And next we need an output to energize. And this is going to be our first alarm, which will use an internal binary bit, B30/0. That's the first channel of our first binary word. And this is going to be our over voltage alarm. And we'll just call this OVALM. And then we can pretty much just copy and paste this for the remaining over alarms. with some changes to the addresses. So the next one, we'll choose N71. N71 is going to represent our current measurement. And we'll just use amps for the symbol. The current limit is going to be a static value of 45. We use the same time base, but we're going to use a different timer. So we'll choose the next available timer. And this is going to be our over current timer. And then we'll just call this OATMR for over amp timer. Choose a time base of 1 with a preset of 5. And then we are going to update our additional registers to reflect this timer. So we just need to update our additional registers to reflect the changes that we're making for this specific alarm. So we'll choose the next available bit within the B30 word. That'll be B301. And this is going to be over current alarm. And we'll just call this OAALM as our symbol. Okay, next we're going to configure our overpressure alarm. So we'll use the next available integer register, which is N72. And we're going to change this symbol to just call it pressure. And we'll call this discharge pressure. This is going to compare the current value against a static value of 325. And if it's greater than or equal to 325, it will start our next timer, which will use T42, which is the next available timer. Time base of 1. We'll update our done bit to match the timer that we are using for this instruction. And then we're going to use the next available bit within the B30 word, which is B302. That's our pressure alarm high bit. Next, we're going to configure our overflow alarm. So this will be the next available integer register, which is N73. We'll call this discharge flow, and we'll just call the symbol flow. This is going to compare the current flow rate against a static value of 75. And if it's greater than or equal to 75, it will start the timer. And we need to choose the next available timer, which is T43. This is going to be our overflow timer, and we'll call this OFTMR. Next, we are going to update our T40 done bit to T43 done. We don't need to populate that since we already did that in the previous step. And this will be the next available bit within the B30 word, which is B303. This is going to be our flow alarm high, and we'll call this FAHH. Next, we are going to configure our low flow alarm. So this is going to use the same integer register for flow, but it's going to use the less than or equal to instruction instead of the greater than or equal to instruction, since this is a low alarm. And we'll use a static value of 15. Then we will need to configure a timer for this specific alarm. So that will be T4, and we'll call this underflow timer. And we'll just call this UFTMR. Base of 1 is good. We'll need to update our done bit. And then lastly, we will need to update our bit within the B3 word, which is the next available bit, B304. We'll call this flow alarm low, and we'll name the symbol FALL. Next, we need to add some logic for our run fail. So that's going to be a little bit trickier than our previous alarm instructions. But the basic idea here is if the motor is called to run and we don't receive a run status on the auxiliary contacts, then we will start an alarm and trigger a shutdown because something is happening with the motor that's preventing it from starting. For some reason, we're not getting our auxiliary contacts. So the way we do that is we use a normally open set of contacts, or in RsLogix 500, it's referred to as examine if closed. And then we're going to use a examine if open for our run status. So the first one is going to be our motor output, and we'll go ahead and use a actual output here, which will be output to 0 for our first available output. And this is going to be our motor start command. So we'll call the symbol here M1 underscore start. Next, we are going to look at the run status, and this will be an actual input. So we'll use input slot 1 channel 0. and we'll call this M1 run status. And here we'll just do M1 running for the symbol. Next, we will need a timer. So we can copy a timer from a previous instruction, paste it directly below, but we will need to make sure it is after both of the contacts that we have just added. And we will need a branch around the timer so that we can energize our alarm coil. And the way we do that is by adding a set of contacts and a additional coil for our alarm. So this timer is going to be the next available timer, which is T45. We'll call this start fail timer, and then we'll just call it ST_TMR for the symbol. This will be base 1, preset of 5 is okay, and we're going to use the done bit of this timer to energize an alarm output. And for this, we're going to use the next available bit within the B30 word, which is B305, and this will be M1 fail to start, and we'll call this M1 FTS for the symbol. And next we want to latch this so that the motor is locked out until it's reset by an operator. So the way we do that is by adding a branch below both of our input contacts to our timer. And we're going to latch this circuit in with the B305 bit. And the only way to reset that is by clicking on a reset bit. So we're going to use the same B305 address along with a B306 address, which we're going to use as our reset command. We'll just call that RST on the symbol. Okay, now that we have all of the alarms configured, we can go ahead and verify our runs, make sure we don't have any errors. So everything looks good so far. The next thing we want to do is compare all of these alarm bits and trigger a common fault so that we can use that within our motor control logic and shut down the motor if any of these faults occur. So the way we do that is with a branched OR circuit. So we'll go ahead and add a set of contacts here, which is going to look at the first bit of the B30 word. Then we're just going to add a branch around that bit for all of the remaining B30 bits. The way we do that is by extending the branch down, and we will need a total of 6 here for every alarm. And then we're just going to add our open set of contacts for each bit. Okay, so we have all 6 alarms, and the next thing we need to add is a common fault coil so that we can energize this fault coil if any of these alarms occur. So this will be the next available B3 bit, which will be B307, and this we'll just call common fault, and for the symbol we'll just use the word fault. We'll go ahead and verify that, make sure we don't have any errors. And next we're going to build our motor circuit. So the first thing we want is an emergency stop. That's common practice with motor controls. Generally you have a normally closed push button that when it's pressed, it opens the circuit and de-energizes everything downstream of that circuit. It can be hardwired or it can be done programmatically. It can be done either way. So we'll use the next available bit within the B30 word, which is B308. And this is going to be our stop. And we'll just call this e-stop on the symbol. Then we need a start command, which will also be a bit within the B30 word. And so we'll use the next available. And that'll just be our motor start. And we'll just call this start_CMD. And next we need our motor output, which is going to be equal to the motor output that we already configured. So that is O2 channel 0. So output slot 2 channel 0. So we'll use the same output. And that is our motor 1 start coil. So this is the actual output that will go to the auxiliary contacts on our motor starter and will energize the auxiliary contacts, which will in turn energize the motor contactor and start our motor. We want this to be a latching circuit, meaning this start command here is just a momentary contact push button, not a stationary. So when we press this one time, we want our motor to stay running until there is either a fault or the emergency stop is pressed. So we're going to go ahead and add our fault, which is B307. Next, we're going to add a branch around our start command, which is going to look at the status of output 20 and latch in the circuit unless either a fault is detected or the e-stop is pressed. So this, we'll go ahead and use output 20, and we'll verify that branch. And so now we have a basic motor control program that is looking at a series of alarms. And if any of those alarms occur, it will trigger a fault, which will shut down the command going to our motor. Okay, now we're going to download and go online so that we can test the changes that we've made to this program and verify that our motor control logic is working correctly. So I'll go ahead and put this in run mode. And first thing we want to do is just go through and configure some of these values. So N70 is our voltage. We'll set that to 480, which is typical voltage for this type of circuit. Then we'll use 20 amps. We just want to make sure it's below the upper limit. Pressure we'll use 250. Flow just needs to be in between 75 and 15. So we'll just do 45 there. And so now everything is ready to go. You can see that we don't have any alarms active, so our fault is not true. And so now I can toggle my B309 bit, which is going to energize the output. So the next value that we want to toggle is going to be our run status, so that this fail to run will not get triggered when we start our motor. So we'll toggle that bit and verify that we don't currently have any faults. Our fault bit is false. And so we have continuity across our e-stop, we have continuity across our fault, and now we're just waiting for a start command. So I'll toggle that bit to start the command. I can toggle it off and you can see that my motor is still running because we have this latching circuit below it. So now I can trigger some of these alarms so that we can verify that they're working properly. So the first one we'll do is over voltage, and this just needs to be above 520. So we'll go ahead and use 525 as the value, and you can see that my accumulated value is increasing, and it has triggered the B300 bit, which is the over voltage alarm. So now if we scroll down to our fault logic, you can see that B300 is triggering B307, which has energized the fault bit and has de-energized the motor according to this logic. So that is what we expect, and we can clear that alarm by lowering the voltage value below 520. So we'll put it back to 480, and you can see my alarm went away. That's a non-latching alarm, self-clearing, and my fault has also cleared itself. So we'll go ahead and toggle our start command again, and we will trigger another alarm. So we'll go ahead and use current this time. This just needs to be above 45. So we'll use 50, and you can see my accumulated is increasing, and my fault bit has energized, which has opened the circuit and de-energized my motor output command. So all of these alarms pretty much function exactly the same as the first two that were demonstrated, except for the fail to start alarm. So we'll go ahead and clear our overcurrent alarm by setting the current below the current limit. So we'll set that to 30. We'll verify that our fault is no longer active. We will toggle our start command, which is going to start our motor. And then next we're going to toggle our run status. So what this is simulating is a open set of auxiliary contacts, meaning the auxiliary contacts that are on the side of the motor contactor that indicate whether it's running or not are going to be toggled, so that even though we're issuing a motor start command, the run status coming back from the motor is false. So we'll toggle that, and we'll see that our timer is increasing, and B305 fail to start bit has gone true, which has triggered our fault bit, which has then de-energized our motor control circuit. Thank you for watching, and I hope this helps.